Let's do another example. Here we have to find the arc length of the parabola y squared is equal to x, right? Now in this case also we can either subject y from the given equation, which is y is equal to x to the power half, but see in the way that they have given the equation itself, we can visualize this one as an equation which has already subjected the x variable, so we can use it like that directly, right? So we have written down x as a function of y, which is equal to y squared. So what we have to do is, for the length we can consider f as our function that runs through the y variable. That's the function that we should include or insert in our equation, right? So this function f prime this function f inside f prime represents the relationship between x and y, and one should be written as a function of the other. It can either be x written as a function of y, or y can be written as a function of x. And remember, in the previous example we did a case where y is written as a function of x, and here we will deal with the case where x is written as a function of y. But still, in this case also we can rewrite y as a function of x and compute everything by considering fx as x to the power half. Then again you should get the same answer, right? But in my example, in my working, I will consider x as a function of y, which is y squared, right? So now to find the length, we just have to use this formula, 1 plus the derivative of f with respect to y, and remember we should square this one, okay? And here we have a square root, and then the integral runs through y variable, and we should find the length from 0 0 to 1 1, 0 0 to 1 1. And since the integral runs through the y variable, we have to consider the start point and the end point of the 1 variable. But of course in this case both are the same, right? Both x and y coordinates are the same, but be careful, you should choose the correct y variables at both start and the end points, right? Okay, now we just have to evaluate the derivative first. We will do it separately. So since fy is equal to y squared, that implies the derivative is equal to f prime y is equal to 2y, and so if we substitute that in our length formula, then it becomes this one, right? So now remember, here we have a square root, and in the previous sections we did, if we have this format, we have to use the substitution of x equals a tan theta. But in this case it's not the variable itself. Here you have 2y squared, okay, but here it should have the variable squared, okay? So what we can do is we can consider u as 2y, so therefore we have 1 plus u squared in the square root. So that means what we can do is we can subject u as 1 tan theta. In other words, 2y as tan theta. That is y is equal to half tan theta. So this should be the correct substitution. And if you need if you are not clear with this calculation, please refer the video set related to the previous chapters, right? And then with this substitution we can simplify the integral. The simplification will be like this, right? So once you have the given substitution, the square root term can be written like this. And remember, we are dealing with a very specific range of the angles, and then we have to convert everything back into y variable this is originally in y variable, and we have to convert everything in terms of theta. Here also we need the corresponding d theta value, and that can be obtained by differentiating the above equation with respect to theta which is equal to dy by d theta equals to half sec squared theta. In other words, dy is equal to half sec squared theta d theta right? Okay, and with that information we can now directly plug in the values for the length equation. And here we can see for the lower limit, when y is equal to 0, the theta value will be equal to 0, and for the upper limit we have a problem, right? See, when y is equal to 1, which is our original upper limit, what we can, like, the only thing we we cannot get a nice angle like this by substituting y equals 1 in our formula, okay? Because when you substitute 1, it becomes tan theta equals 2, so we don't have a exact answer from those tables for tan inverse 2. Then what we can do is we can just keep it as tan inverse 2, right? And it will make it easy for the simplifications if you just rename this as another variable. Let's call it as alpha, or else you can keep it like tan inverse 2, but since it has got so many letters, it will be very convenient if you use a single notation to represent tan inverse 2. Okay, so in these integrals you can nicely write this alpha notation without taking much space, right? So the integrals will be like this, and then now for this one, here it will be sec cube theta, and from here to here we don't have any standard formula to integrate sec cube theta. But in previous examples, exactly on example 7.2.8, we discussed how to obtain this answer. I mean the answer of sec cube theta. When you integrate it, you will obtain this one as the answer, and we discussed it in the example 7.2.8. You can see it in our videos as well as in the book. Like, you don't have to remember these formulas, okay? But only thing is that you have to know the method, the correct method to obtain these formulas, right? Okay, so once you have this one, now here you have the alpha, and then you can substitute upper and lower limits, right? For the lower limit you have 0, and that won't make any problem, right? Because tan theta will be 0, right? And when you have this one, I will rewrite it with alpha. See, instead of tan inverse 2, I am writing alpha, okay? Because then it's easy to proceed with the other calculation. And here you can see what you have is tan of tan inverse 2. That's like going forward and backwards, so you end up with the original position, which is equal to 2, right? And basically if you just represent it as alpha from the this equation also, you can see the same result. See, we have represented tan inverse 2 as alpha. In other words, alpha is equal to in other words, if we take tan into this side, 2 is equal to tan alpha, right? So tan alpha is equal to 2, right? That's the same thing that appeared in here. See, if we represent tan inverse alpha as 2, so together with this tan outside, you have tan alpha, which is equal to 2, right? And for the other term, you have sec alpha plus 2. And then for this one, we can do one more thing, right? We know that tan alpha is equal to 2, and also we have this trigonometric identity, which is tan squared alpha is equal to sec squared alpha. Therefore, sec alpha is equal to 1 plus tan squared alpha square root. That means 1 plus tan alpha is equal to 2. Therefore, this becomes 4 square root. So that means sec alpha is equal to the square root of 5, right? So we can replace sec alpha with square root of 5. So this becomes now this 2 and this 4 will be simplified, so it becomes half, and for sec alpha we can write square root of 5, and inside the logarithm we have square root of 5 plus 2. Now this 1 over 4 should come here as well. Okay, so we have it over 4, right? So this will be the arc length from 0, 0 to 1, 1 position of this given curve. The given curve is y squared is equal to x. This is a parabola, right? Okay, and from the next video we can finish the section 8.1.